Okay, so I guess to start, you do have a quiz next week on Wednesday, I'm pretty sure. I'll post an announcement later today on exactly what's being covered. It does include some of the bash stuff that we didn't, that you weren't tested on in the first quiz. So basically loops and arrays and bash functions. And then there'll be a small amount of fundamental C, but nothing terribly complicated. I'll also post a sample quiz so that you can look at that for reference. Today, the plan is to finish off the arrays notebook, and then you may have noticed the notebooks are incomplete. That's because this is still a work in progress. So I'm going to switch to PowerPoint slides for the rest of the lecture, and I will post the updated notebooks on the weekend. All right, so we're talking about arrays. Now, when you pass an array to a function, the C doesn't pass the entire array to the function. So it's mostly because the overhead of passing the array is too high, right? So if you wanted to pass an array by value to a function, you would have to copy the entire array over to the function. The other problem is if you did pass an array by value to a function, if the function changes values in the array, then the caller wouldn't have those values changed in their array, which is also, and usually it's the case when if a caller is passing an array to a function and the function is supposed to change the array, the caller wants the array to be changed, right? They don't want to get back a copy of the array because, again, there's all this overhead with copying the array. So what happens in C is if you write a function with that declaration, right? So you say that your function takes in an array as one of its parameters, the compiler changes that. It changes it to the following. Right? So it changes it to, your function now takes in a pointer to an int. Right? So rather than taking in an array of int, it takes in a pointer to an int. And when it calls the function, and if you call the function, what ends up happening is you get the function gets a pointer to the first element of the array. Right? And so that saves the overhead of copying the array. Now you're just passing a pointer. Furthermore, the function can change the contents of the array, which may or may not be desired. Right? If you want the function to not change the array, then you should declare the array to be const. Right? You should make that const int array square bracket square bracket. Right? Okay, now there's one of the immediate consequences of the compiler changing your array to a pointer is that size of no longer works, right? So here we have an array of length 100, and we call the function f, passing in the array to the function. Now inside the function, notice that the function doesn't get the length of the array, right? The function is declared as taking in just an array. And remember that when the function is called, the array that's passed in degrades to a pointer to the first element. So when you ask for the size of the array, you no longer get the amount of memory required by the array. What you get is the amount of memory that's required by one pointer, right? And the amount of memory that's required by one pointer is always a constant value, right? On my computer, it happens to be 8, right? So if I run this code, why does this, standard, sorry. Include standard, standard IO is there. What's the problem? Size of, will return. Oh, never mind, sorry, it's fine. It's just warning me. Why is that a ZI? Anyway. It's warning you of using size of. So it says in the function f, warning, size of an array function parameter will return size of int star. Right? In other words, it's going to tell you what the size of the pointer is. It's not going to tell you what the size of the array is. When it prints out the length, it thinks it's 2, right? Because the size of a pointer on my computer is 8, and the size of an int on this computer is 2. So you end up with 4. 4, right? 2. Sorry, that's 8 and 4. So the size of a pointer is 8 bytes. The size of an int is 4 bytes. So you get 2, right? You don't get 100, which is the correct size of the array. So whenever you have an array as one of your parameters to a function, you almost always have to add a second parameter that says what is the size of the array. Right? So there really ought to be another parameter either before or after the array that indicates how big the array is. Okay, so there's several ways to solve the problem. One is to add another parameter for the length of the array. Right? The other way to do this is your array has to have a special value in it that indicates that there are no more elements in the array. That's how strings work in C. Right? So the reason strings have to have the digit 0 at the end of them is to indicate that's the end of the string. Right? Because there's no way that you can, the compiler has no way to determine what the size of an array is when it passes it to a function. So here's an example of max that uses, right, here's max that computes the max of that array, right? And it has a second parameter that says how many elements are in the array. Right? Notice that the array is declared to be const. Right? So max is saying that it's not going to change the contents of that array, right? Which is nice. Now, otherwise, max is just, it's easy to compute the max, right? You just loop over the array, right? And if you run it, it works just fine. Right? But there's no way for you to know, right? But there's no way for the function to know how big is that array unless you tell it, right? So you need an extra parameter. So we use an extra parameter in this case. Notice there's a side effect of this passing in the length of the array, right? Suppose you only wanted the max of the first 3 elements, right? Then you don't have to pass in the full length of the array. You can just pass in 3 now, right? And now you've got a function that computes the maximum. So let's do 2 instead. So the first 2 elements, right? And now you've got a function that can compute the maximum element for the first part of an array, right? Not necessarily over the whole array. And that might be useful. Okay, so that's what happens when you pass an array to a function. There is another way to pass an array to a function. So for example, you can do the following. Let me just change this. So I'm just going to switch the order of the parameters. And then I'm going to do this, like that. Right? So you can try to tell people that this array needs to have that length, right? Or sorry, let me do it a different way. Let's try it a different. No, let's do that. That's fine. Let me just add a second one. So void some function f takes in some array of double 5, right? So that function declaration right there, or that function f, says that it takes in says that it wants to take an array of double of size 5, right? Right, that's what it says. However, if you were to try to call this function, when C calls the function, whatever array you pass in, const double, sorry, const, sorry, that's not right, AR, there we go. Okay, so when C calls the function, the array still degrades to a pointer to the first element, right? So in other words, your compiler, as far as it's concerned, still thinks that this function is actually void f const double star. Right? So in other words, even though you're saying it's an array of size 5, the compiler doesn't care. It's still going to treat it as though it was just a pointer to a double. And so it still degrades. So in other words, that 5 is not enforced at all. Right? You can make an array of size 1 and pass it to that function and it'll work just fine. Right? You can make an array of size 1,000 and pass it to the function, and the function will still, C will still call the function without any issues. Right? So even if you specify the size, that size is not respected at all by the compiler. Right? It's just there for, it's just there to tell other people this function is expecting an array of size 5. But the language is not going to check that for you. All right, what happens if you return an array from a function? Right, so returning an array from a function, the same thing happens. Right, so if you return an array from a function, it does not copy the array and return a copy of the array. It returns a pointer to the first element of the array. Right, so the returned array still decays to a pointer of the first element of the array. Right, now what's the implication of this? Right, so number one, whoever gets back that array doesn't know how long that array is. Right, so if your function returns an array, it must also convey how long is that array somehow. Right, because there's no way for you to get back the length of the array that's returned, because all you're really getting back is a pointer. So that's problem number one. Right, there's many ways to solve this problem. Right, one way to solve the problem, right, add another parameter that the function can use to store the length of the array. Right, so in other words, try to return two values. Right, return the array as one value, or return a pointer to the first element of the array as one value. And then your second value that's returned, you're going to have a parameter that's a pointer, and you're going to write into that object that's pointed at by that pointer to return the value of the, to return the length of the array. Right. Solution number two. You can return an array, and one of the elements of the array, you can return an array, and the array has a special value that indicates the end of the array. So that's how C strings work. Right? If you if you call the function that returns a C string, typically the function will write a null terminator, the digit 0, into the end of the string. Right? So that's another solution. That doesn't always work, because sometimes many times, there is no appropriate special value. Number three. Instead of returning a pointer to the first element of the array, you can return the length of the array, and you can ask the caller to provide an array that you can write into. Right? So now the caller is responsible for providing storage for the array that's returned. Right? So that's another solution. And finally, another solution, you can return the length of the array, and you can require the caller to supply a pointer to a pointer. Right? So in other words, your function is going to look like the following. So you're going to return the size of the array. So that'll be type size t. You have some function, right? And if you want to return if you want to return an array of int, you can return one of these things instead. Right? So you can return a pointer to an int. Right? So what you're going to do here is you're going to dynamically allocate an array, right? Which I'll show you how to do later in this lecture. Right? And then you're going to return a pointer, you're going to return a pointer to the pointer that points at that array. Right? So you have this double star here. I don't think I actually show you an example of this ever in this course. As soon as you start working with pointers to pointers and pointers to pointers to pointers, things become very confusing. Yes?
How many levels of pointers are there?
There's no set limit.
Oh, okay, so you can have like 20 pointers.
Yes, you could. The general advice is never write a function that someone else has to call if there's more than 2 stars in front of it. Yeah, that's the general advice. Okay, so let's look. What does this one do? Functions that return C strings. Oh yeah. Okay. So if functions that return strings, they always use a special value to indicate the end of the string. We can't actually do any of these options yet because we don't know how. So an incomplete example of the first option. So option number 1, add another parameter that the function can use to store the array, length of the array. Right? Okay, so some func here. So that's going to return an array of type int, right? So it's going to return an array of int. So it can't return an array of int. It has to return a pointer, right, to the first element of the array. Oh, I forgot to mention. You can't write square bracket here. The compiler won't let you. So you actually cannot return an array from a function. you have to return a pointer. This parameter here, right, is a pointer to a size t object. Right? So the function is going to write into the object pointed at by length to return the length of the array. Right? So up here, we're going to make an array of some length y, right? And then that's the thing we're going to return. Right? Notice it's not shown for a reason, and we'll go through an example in a moment. Right? I'm going to store the length of that array in the length. Now length is a pointer, so I have to dereference the pointer and then store the value, right? And then we'll return a pointer to the first element of our array there. Now whoever calls the function does not call it this way, sorry. Whoever calls the function is supposed to call it as, why are we using max? Sorry, this example is completely wrong. So whoever calls the function is going to call it like so. So they're going to get it back an array, some func, and length. Like that. Right? So to call the function, they need to provide a pointer to a size t object where the function can write the size into. Right? So we need a variable of type size t, right? Not a pointer here, right? You don't want to use a pointer here called length. You need an object of type size t called length, and you want to pass in the address of that object. Right? And then when the function returns, you'll have an array, and you'll also have the length of the array stored in len. Okay. So the reason why that I didn't show you how to make the array is because of how arrays are handled in C. Right? So suppose some func was implemented like this. Right? So I'm going to return an array of size 100. So I set y to 100. Right? And then I make an array like that, right? Which works. So that's what's called a variable length array. Right, so a variable length array is an array where the length is specified by a variable, right, and not a constant value, which is allowed in since C99, I think. So that makes an array, and then we write the 100 into length, and then we return array, right? So remember what that returns. That returns a pointer to the first element of that array. Right? So in other words, it returns the address of ARR0. Right? What's the problem with returning the address of ARR0? Right? That's a local variable. Right? So it has automatic storage allocation. Right? What does that mean? It means that variable doesn't exist when the function ends. Right? The scope of this variable, the lifetime of this variable starts here, and it ends right there. Right? So that array doesn't exist when this function returns, and you've returned a pointer to that array. So when the person who called the function tries to dereference that pointer, bad things happen, because that array doesn't exist anymore. Right? It's gone. Right? So some func attempts to return a pointer to an object having automatic storage duration, and that means it's guaranteed not to exist after the function returns, right? Or is not guaranteed to exist after the function returns. If you try to dereference the pointer by using array indexing or something else, right, you're almost certainly going to, almost certainly something bad will happen. Right? Okay. So that's the end of that notebook. Now we need to actually figure out how can you actually return an array from a function, because it's something you're going to want to do. Right? And so for that, I'm going to switch to a PowerPoint slide. So this is the set of slides called More Arrays. They are available on OnQ. It is there. Right. And then I'll update the notebook so that information is actually inside of a notebook somewhere. Okay, so C99 introduced this thing called the variable length array. Right, now variable length doesn't mean you can change the length of the array. It just means that the size of the array is specified by a variable. Right, so once you make the array, it still has that size. Right, so for example, right, right? That's an array of length n, where n is a variable. Right? In C, there are no such things as zero-length arrays, so you can always do array 0, or you're always supposed to be able to do array 0. Right? So to print an array, we can write the following code. Right? Print the opening square bracket, and then the first element. Then print a comma and a space and every other element. Right? And then closing square bracket at the end of all of this. Right? So here ARR is a variable length array. You can also make one inside a function somewhere. Right? So you can write int ARR some variable n, as long as n has an integer type. Oh, there's a variable length array right there. So this program here is going to ask the caller. It's going to run, and then it's going to prompt the user to enter in the size of an array. Right? So it's going to ask for an array of size less than 20. Right? We're going to use scanf. I'll explain in a second. Scanf is what's going to read the keyboard for input. Right? If the result is between 1 and 20, we'll make our little array. We'll fill the array with the values 0 up to, but not including n, and then print the array. Right? So if you run that, where is it? Like that. Right? It asks for an array size of less than 20, so let's do 17. Right? So it makes an array, populates the array with the values 0 through 16 and prints the array. Right? So that's an example of a variable length array. Now, size t, I think I've explained this before. So it's an unsigned integer type that is that size of returns, and it can store the maximum size of any theoretically possible object of any type. Right, so if you want to describe the size of something, then size t is normally the type of variable that you would use. Scanf we haven't seen yet. So scanf is like printf, except where printf prints stuff to standard output, scanf reads standard input. Right? So it reads information from standard input, and it tries to convert the information it reads using the similar set of conversion characters that printf uses. Right? So here, scanf, so read standard input. Right? It's going to try to read one value from standard input. Right? And it's going to try to convert that value as though it were a long unsigned value, which is normally the size of size t on most computers. Right? Right? So formatted, so read in formatted information from standard input. Right? You can have as many conversion characters here as you conversion symbols here as you want. Right? For every conversion symbol here, you have a corresponding argument over here. Okay, if it works, then it stores the converted, it stores, oh, sorry, let me back up. So when you read standard input, it's always a string, right? It's always a sequence of characters. And so this conversion here tries to interpret the sequence of characters as though it were a type of that argument there, right? So n has type size t. You need to pass it a pointer to the object where you want to store the value in, right? So it needs a pointer to the object where you want to store the value in. So if we pass it a pointer of type size t, right, we can store a long unsigned value in that object. Right? If you wanted several different objects, if you wanted to try to read in several different values, you can put in additional conversions here, and then you would create more variables in which to store the converted values. So if the function is successful, it stores the information in the objects that are pointed at for the arguments that you pass in. It returns the number of successfully converted arguments. Right? So in this case, returns the number of successfully converted arguments, or, oh, sorry, result. That should be n. Oh, no, if result is 1, right. Returns the number of successfully converted arguments. So this is checking, did scanf actually read in an int, an unsigned integer of some kind, right? So did it manage to successfully convert the string into an unsigned int, right? So if result is 1, right? And if the value that it read in is less than 20, go ahead and make the array. Okay, so regular arrays and variable length arrays, they all have automatic storage, right? So their lifetime is the lifetime of the block that they're defined in. And that means you can't safely return a regular array or a variable length array from a function because it doesn't exist after the function returns. So here's my make array function, right? So this time instead of making a little local array here, I'm going to try to call a function that makes an array, right? So to make an array, I'm going to do the same thing I just did before. I'm going to make an array of size n. I'm going to fill it with some values, and then I'm going to return the array, right? Remembering that you're going to return a pointer to the first element of the array, right? That's a problem, right? Which is why the comment is here, right? It has automatic storage. So it doesn't exist after the function returns, but you've returned a pointer to that array, right? So you've returned a pointer to memory that is no longer guaranteed to exist after the function returns. So when you try to print the array, what does it do? Right? It dereferences the array, right? It dereferences the pointer. So this is almost certainly going to barf when you run it. So this is array lifetime. Okay, so 17. And it barfs, right? Notice it doesn't say anything useful at all, right? It doesn't tell you that the array doesn't exist, right? It doesn't tell you that you've gone out of bounds. You just get this error that says segmentation fault, right? A segmentation fault is an indication that you've tried to access memory that is no longer, what's the best way to put this? Well, it's no longer valid anyway, right? And so your program just crashes, and now you have to figure out where on earth did my program just crash? Because it doesn't tell you that either, right? Whereas in Python or Java, when you get an exception, it tells you exactly where the exception has occurred. It even tells you what sequence of events caused the exception to occur. Here, you just get segmentation fault, right? And so good luck trying to debug your program now. Okay, so what happens if you want to return an array, right? It seems like this is something you're going to want to do. And so the answer is you now have to use what's called dynamically allocated memory, right? So dynamically allocated memory is memory where the programmer controls the lifetime of the memory, right? Statically allocated, objects with static allocation or static or automatic storage duration, right? The C language takes care of the lifetime of those objects. With dynamically allocated memory, the programmer controls the lifetime, right? And so anything where you want memory to grow or shrink, like in a stack or a queue or some sort of data structure, right? You probably want dynamically allocated memory, right? Certainly the memory for those data structures should not have automatic storage duration, right? So in other words, you shouldn't make a local array for those objects to write into, right? Because that array is not going to exist once that function returns, right? Similarly, you don't want these type of data structures, normally you wouldn't want these data structures to have static storage duration either, right? So remember, static storage duration, the object lives for the lifetime of the program, right? But if you want to make more than one list, right, you now need to know that there's going to be more than one list in your program, and you have to make a static variable that corresponds to the second list, right? If the number of lists in your program might vary, there's no way for you to use static storage duration. There's no convenient way to do it anyway. Okay, so dynamically allocated memory has what's called allocated storage duration. So in allocated storage duration, the lifetime of the object begins when the memory is allocated for the object. It ends when the programmer says so, right? So the programmer has to do something specific to end the lifetime of that object. So dynamically allocated memory is managed by the operating system, right? It's not part of the C language specification, And so different operating systems will implement your memory managers in different ways, right? It's even the case that if you're writing a program that needs lots and lots and lots of memory, it may be advantageous for you to write your own memory manager. But that's way beyond the scope of this course. Right? Okay, so in common implementations of memory managers, the memory allocator uses something called a heap. Right? So the heap is just a big chunk of memory that can be chopped up into smaller blocks of memory. And the memory manager can manage which blocks of memory have been handed out to, or are available. Right? So the way this thing works is you ask the memory manager for a chunk of memory. If it can give you one, it gives you a pointer to the chunk of memory. Right? When it's time, when you're done with the memory, you have to give the memory back to the allocator so that it can give that memory to somebody else that needs to use it. Right? So you're going to use dynamic memory or dynamic allocated memory when the exact memory requirements, you don't know them at runtime, which is the case for almost any non-trivial program. Right? You almost never know how much memory your program's going to use when you start to run it, at least for anything that's not like a school assignment or something like that. Right? Now, one of the issues with dynamically allocated memory is that it's slower than memory memory that is used for automatic storage. Right? So the memory that comes from the heap comes from a different part of memory than the memory that's on the stack, which is where all of your automatic variables live. Right? Stack memory is very fast. Heap memory is slower. The other problem is if the programmer is under control of the lifetime of the object, the programmer has to be careful that they actually release the memory back when they no longer need it. Right? And so it's very easy to write a program where you are constantly allocating memory, but you forget to deallocate memory. Right? And so if your program runs for a long time, eventually you run out of memory and your program stops. Right? And then you have to go and figure out, where did I forget to deallocate the memory? Right? And so when you forget to deallocate memory, that's called the memory leak. Right? And it's one of the most common sources of error in C-like programs. It's also why Java doesn't let the programmer control the lifetime of an object. Right? So one of the reasons Java was created is to get rid of this problem of manually managing memory. Sorry. Okay, so how do you do this? So the good news is there's only 4 functions you need to know about, right? And 3 of them are closely related. Right? So there's malloc, calloc, and realloc. So those are the 3 functions, 3 common functions that you would use to ask for dynamically allocated memory. The one that you call to get to release memory that you've allocated is free. Right? So these are the 4 that we need to know about. Malloc, short for memory allocation, right, will attempt to allocate an uninitialized block of memory of some size. Right? So uninitialized means that the memory could have any value in it. So if you dynamically allocate an array, the elements of the array might have any value. Right? You have to initialize them yourself. When you ask for the size, you have to remember that in C, everything's always measured in terms of the size of car. Right? So if you want an array of int, or if you want a single int, you have to ask for enough memory to hold an int. Right? Malloc returns a pointer to the allocated memory. If the allocator can't give you that memory, malloc returns null. On Linux, malloc never returns null, though. So Linux is a bit funny on how the allocator works. I think so. I know that the notebook for this topic has a discussion of that, so I'll leave it for that. All right. So if we go back to our previous example, instead of making a variable length array here, right? We're going to dynamically allocate the array. So make array should make an array of int that can hold n ints. So the way you use malloc is as follows. Right? So you call malloc, right? I want n ints. So I need enough memory to store n ints, right? So it's n times size of int, because the unit that's used to measure memory is the amount of memory required by car. Right? So whenever you're using malloc, you're almost always writing something times the size of the thing you're allocating. Right? You can allocate a single int if you wanted to. Right? So you could just write malloc size of int, and that'll give you a dynamically allocated int. Right? So if this succeeds, you get back a pointer to the first element of this memory. Right? So that'll give you back a pointer to the first element of the array. And now I can just return that pointer back to the caller. So now if you run this program, right, so everything else is the same, right? The only thing that's changed is make array. Right? So now if we run this program, 17, everything works the way we want it to, right? It doesn't crash anymore, right? Because we're returning a pointer, right, to a dynamically allocated memory. Now notice here, after I'm done with the array, so this program doesn't do anything except print the array, right? So after I'm done with the array, it's polite if you return the memory that you used, right, that you allocated. So to free the array, you just write free and then pass in a pointer to the first element of the array, right? And that will deallocate or return the memory back to the memory manager, right? And so you should always free any dynamically allocated memory once you're done with it. Now inside a main function, that free doesn't really matter, right? Because as soon as your program ends, any memory that was allocated by the program gets released back anyway to the operating system. So typically, you know, that free right there is not actually required in this case, right? It's not going to produce a memory leak in this case, but more generally, when you're done with a dynamically allocated object, you should always free the object. Oh, there's another way to use malloc. So if you don't like writing, oops, sorry. If you don't like writing, sorry, I keep on pressing the wrong button. Okay, if you don't like writing n times size of int, you can do size of and then not make an array. So int square bracket n asks size of to compute the size required by an array of int of size n. Right? So you can also specify it that way if you don't like doing the n times. Right? It's the exact same thing. calloc is the allocator that you want, is the allocation function that you want to use if you need to initialize the memory that you get, or if you want to initialize the memory that's returned back by the allocator. Right? It doesn't actually give you any flexibility on how you initialize the memory. Right? So calloc allocates a block of memory for n objects. So it works a little bit differently than malloc. Right? It initializes all of the bytes of the allocated memory to 0. Right? So for the integer types, it initializes everything to 0. For Boolean, it initializes everything to false. And for double and float, I'm pretty sure everything gets initialized to 0 as well. Again, it returns a pointer. What just happened? Hello? Oh, sorry. Okay. It returns a pointer to the allocated memory if it succeeds, and it returns null if it couldn't allocate, if the allocator could not return, it could not allocate enough memory. Okay, so the way you use calloc, it's pretty similar to malloc, except you pass in 2 arguments. Right? So the first argument is the number of objects that you want memory for. So I want n objects. The second argument is the size of each object. Right? So whereas malloc wants you to ask for the total amount of memory, calloc wants you to ask for how much or how many objects, and what is the size of each object. Right? And so this, if you run this program, again, it works the exact same way as before. Right? If you were to print out the array, oh wait, this one prints out, what does this one do back here? Okay, sorry, let me try something back here. Array malloc. What did array malloc do? I think I'm showing you the wrong code, sorry. Array malloc. Oh yeah, hang on. Let me comment out this loop. Let's run it again. So this is with malloc again. So remember, malloc does not initialize the memory. Right. Oh, okay, so in this case you get back all zeros. Right, so when we allocate the memory, right, you get back an array. In this particular instance, you're getting back an array of all zeros. So it looks like malloc is initializing the memory for you. It's not. Right, you have to be very careful about this. C is really annoying. So malloc specifically says it does not initialize the memory for you, right? But when you run a little toy program like this, it really does look like malloc is initializing the memory to 0 for you, right? It's not. If you were to change this function just a little bit, so I'm going to do the following. So I'm going to allocate that memory, and then I'm going to free it. And then I'm going to reallocate it. Right, so allocate once, free it, then reallocate it. Right? I'm not initializing the contents of the array. Oh, it's still giving me all zeros. Nope, 19. Is it going to get me? Is it going to let me do it? It's not going to let me do it. So again, it still looks like it's still initializing the memory to all zeros. It really isn't. Somewhere the notebook that I wrote actually has an example where you can, when you print out the array, it's not all zeros anymore. Right? So you have to remember that malloc does not initialize the array. calloc does initialize the array to all zeros. So be careful when you're using malloc. Don't assume that it's setting all the values to 0. Oops. Do we have, yeah. So let me just quickly do, let's do realloc very quickly. Okay, so the last memory allocation function is realloc. Right? So it's often the case where you've allocated some memory, and then you realize, I want more memory, or I want less memory, right? So this is what would happen when you allocate an array and you decide, oh, I need a bigger array, right? Which happens whenever you're trying to implement a data structure whose size can grow or shrink and you want to use an array. Realloc will attempt to reallocate a block of memory that was previously allocated by malloc, calloc, or realloc, right? So in other words, if you allocate some memory and decide that you need more or less, you can call realloc on the pointer to that memory, right? And it will try to change that block of memory to a different size, right? So you pass in a pointer to your, typically it's an array, right? So you pass in a pointer to your array, and you ask for and you specify the new size of the array, right? Again, remember the size is in terms of the number of car, right? If it works, you get back a pointer to your newly allocated array, right? Plus all of the elements that used to be in the array are in the new array, right? So in other words, it copies all of the memory that you previously allocated and assigned into the new array, right? If your new array is smaller than the old array, then you get back the first n elements of your old array, right? So they're still intact. If it fails, the original pointer is still valid, right? So if realloc fails, then the original array doesn't get removed or deleted or modified at all. right? So if reallocation succeeds, then the contents of the original array that fit into the reallocated array are preserved, right? The excess memory is not initialized, right? Okay, so here is, again, we're going to make an array using malloc, right? So here, we're going to run our program, make an array, we're going to print the array, and then we're going to ask the user again, right, for the new size of the array, and we're going to reallocate that array, right? So the way you use realloc is you pass in a pointer to your array, and then you specify the size that you want your array to have now, right? So this will let me shrink or grow the array in this case, right? Okay, so let's make an array of size 10. So there are my elements. And now let's shrink the size of the array down to 5. Right? And so now you get back the first 5 elements of the array. Right? Similarly, we'll make an array of size 1. Right? So it's got the 0 in it. And now I would like an array of, I'd like to reallocate it so that I can store 19 values in it. And there you go. Oh, this is perfect. Right? Notice that when you reallocate it, not all the values are 0. Right? So any of the new values, right, they lose. They could have any value. They could have any arbitrary value. In this case, it's 132401. If you were to run it again, you're going to get a different result. So 1 and then 18, right? And oh, it's still the same number. Well, I guess I was wrong, right? So it's but the memory that gets the new additional memory is uninitialized. Right, so you now have to go in and if you need it to be initialized to some value, you have to go in and set it yourself. Right, and so those are the 3 dynamic memory allocation functions. Right, and we'll actually use those to implement some data structures probably in a few lectures from now. All right, that's it for today. Are there any problems? I'm trying to remember. There might be some issues with the lectures from this week. I don't know if they all recorded. So if they haven't, I'll have to re-record them this weekend, and I'll post them later.